In this example, we've got a ball that's rolling down a semicircular hill. It starts up here at the top, at state 1, then it starts rolling, and we want to find the velocity of the ball at state 2, which is at some angle as that it's rolled down the hill. If we're given that it starts from rest, we are given radius of the hill, radius of the ball, mass of the ball, and angle, theta, that it's gone through so far. We need to find velocity of the ball at that point. So let's put some numbers in here. Let's say radius of the ball is 0.5 meters and radius of the hill is 10 meters. So the hill is a lot bigger compared to the ball. Theta is 45 degrees. And then the mass of the ball, we'll say, is 1 kilogram. Well, steps to solve this problem. First, we need to know how much this little ball has rotated compared to how far down it's gone along this hill. So let's just call its angle of rotation is going to be delta. So we need to relate delta and theta. And 2, we know that energy is conserved because there's no external work done. So we'll use conservation of energy to find angular velocity. And then finally, we can use the angular velocity to get the linear velocity. Now, somewhere along the way, we'll have to find moment of inertia because that'll go into the energy equation, but we'll get to that. So first, we need to relate delta and theta. So well, we know that this is almost like 2 gears because if the ball does not slip, then the distance that it has spun is related to the arc length that it's traveled through down the hill. So the distance that's been traveled by a point on the edge of each surface is going to be the same. So for that, we know that r times theta equals little r times delta. So delta equals theta times big R over little r. In reality check here, we know that since big R is bigger than little r, delta is going to be bigger than theta. And that should make sense because the ball is going to spin around itself a lot more times before it gets to the bottom. It's going to travel over this quarter circle, but it's going to have made lots of revolutions. So reality check, that looks pretty good. So we can say that we put the numbers into here, then delta is going to be 45 degrees times 10 over 0.5. So that is 900 degrees. Now, 2, conservation of energy. We need to get angular velocity theta dot, and then we can get linear velocity v. And just to clarify, v is center of mass of the ball. So if we do conservation of energy, then we know energy at 1 plus work from 1 to 2 equals energy at 2. But since energy is conserved, this is 0. So at the top, it's not moving because it started from rest, but it has some potential energy. So let's say this is X, this is Y. Then we know that potential energy at 1 is going to equal the energy at 2, which at 2, it'll have some potential energy still because it hasn't got to the bottom. But it'll also have kinetic energy. It will have the translational of the center of mass. But it'll also have rotational because it's spinning around itself. If it was just a block, then it would only have translational because it wouldn't be rotating. But since it's a ball, it's got the rotational. So for potential energy, we know up at the top, it's going to have mg, r. That is the potential energy at the top. Now at state 2, it's only going to have gone, it's only at this height. So this is going to be r cos theta, is that height. So mg r cos theta. So this is going to be plus 1/2 m v squared plus 1/2 I omega squared. But now we need to get rid of a lot of the things that we don't know, so we can boil this down to just one unknown, theta dot. Well, we know that v equals r theta dot for the linear velocity, and omega equals delta dot. And we see over here, taking the derivative of the delta equation, then that equals theta dot times r over r. So if we plug those in, then we have mg r cos theta plus 1/2 m r squared theta dot squared for the linear plus 1/2 I, which is 2/5 m r squared times omega squared, which is theta dot squared r squared over r squared. So now we can cancel some things. So on the left side and the right side, we can get rid of m. And here we can cancel the 2's and the little r squares. So rewriting this, we get g r times 1 minus cos theta. Putting both the potentials on one side and then the kinetics on the other side, we have r squared theta dot squared times 1/2 plus 1/5, which equals 7/10. So now we can actually cancel one of these r squareds with the r on the other side. So we rearrange and get theta dot equals g times 1 minus cos theta times 10 over 7 r square rooted. equals 0.64 radians per second. So that's how we got theta dot, but really we need to get V. Well, we know from above here, 3, V equals R theta dot equals 10 times 0.64 equals 6.4 meters per second. So this is the speed, but if we want to get the velocity, we need to include the direction. Well, if we look up here, V is going to be perpendicular to R, because it goes in the direction of motion. So breaking it down into components, because this angle right here is theta, then we know that V, the vector, equals V, the speed, times cos theta in the I, minus sine theta in the J, which equals 6.4 times 1 over square root of 2 I minus 1 over square root of 2 J, which equals which equals 4.53 I minus 4.53 J meters per second. That is linear velocity of the center of mass of the ball. So to recap what we did for this problem, first, we related the distance that the ball spun to the distance down the hill that it had gone. Then we plugged those geometric relationships into the conservation of energy equation to boil it down to one unknown, theta dot. Then once we found theta dot, we converted the angular velocity to the linear velocity using the radius and the direction.